There's a place in the night sky where the rules of the cosmos seem to bend, where the ordinary gives way to the bizarre, and the familiar becomes utterly alien. Just beyond the Milky Way, drifting like a ghostly smudge of light, lies the Small Magellanic Cloud. This dwarf galaxy, a satellite of our own, is a treasure trove of cosmic oddities, packed with objects so strange they defy everything we think we know about the universe. Imagine a realm where stars behave in ways that shouldn't be possible, where mysterious structures flicker and fade like cosmic illusions, and where entire clusters of matter exist in states science can barely explain. This isn't science fiction, it's real, and it's happening right now, just 196,000 light-years away. What makes the Small Magellanic Cloud so extraordinary? For starters, it's a galactic underdog, a tiny, irregular galaxy that shouldn't hold nearly as many secrets as it does. Yet, within its sparse, sprawling arms, astronomers have stumbled upon some of the most baffling phenomena in the known universe. From rogue black holes lurking undetected to nebulae that glow with no clear source of energy, this little galaxy is a puzzle wrapped in stardust, and today we're going to dive deep into its strangest enigmas, 30 objects so peculiar they'll make you question everything you thought you knew about space. Think of this as a cosmic scavenger hunt, a journey through a galaxy that feels almost designed to keep us guessing. Some of these objects are ancient relics whispering secrets from the dawn of time. Others are destructive anomalies tearing through the fabric of reality itself, and a few, well, we still don't know what they are. But that's the thrill of exploration, the moment you realize the universe is far weirder, wilder, and more wonderful than we ever imagined. So buckle up, because we're about to venture into the unknown, one strange object at a time. By the end of this, you'll never look at the night sky the same way again. The first stop on our journey through the Small Magellanic Cloud's strangest objects is a place where starlight and shadow dance in an otherworldly display in NGC 346, a nebula that shouldn't exist the way it does. Picture a vast, swirling ghost of gas and dust, lit from within by newborn stars so massive they dwarf our sun 100 times over. But here's the mystery. This nebula burns brighter and fiercer than anything its size should allow, like a candle suddenly erupting into a bonfire. Scientists call it a star-forming region, but that barely scratches the surface of its strangeness. Most nebulae of this kind fade as their stars age, but NGC 346 keeps glowing with an almost unnatural intensity, as if something hidden, something we can't yet see, is feeding it energy from the shadows. What really sets this nebula apart are the stars born within it. These aren't just ordinary young stars, they're cosmic titans, some of the most massive ever observed, burning so hot and fast they rewrite the rules of stellar physics. And yet, they shouldn't exist here at all. The Small Magellanic Cloud lacks many of the heavier elements found in galaxies like ours, which means forming such colossal stars should be nearly impossible. But NGC 346 laughs at those expectations, churning out stellar giants like a factory defying gravity itself. Then there's the gas, great looping tendrils of it, twisting through space in braids and knots that resemble cosmic handwriting. These swirling patterns aren't just beautiful, they're clues. The nebula's structure suggests violent collisions, shock waves from exploding stars, and maybe even unseen gravitational forces tugging at its fabric. Some researchers think this nebula could be the key to understanding how the Small Magellanic Cloud has managed to keep forming stars despite its sparse resources, like a desert somehow sprouting a rainforest. But the biggest question of all, why here? Why does this unassuming dwarf galaxy host something that defies so many of our models? Every flicker of light from NGC 346 feels like a taunt, a cosmic riddle waiting to be solved. Perhaps it's a relic of a long-ago galactic collision, or maybe it's tapping into forces we don't yet comprehend. Whatever the truth, one thing's certain. In a universe full of wonders, this ghostly nebula stands out as one of the most beautifully bizarre. And it's just the beginning. Drifting through the Small Magellanic Cloud like a cosmic fugitive, there's a star cluster with a past shrouded in violence, Lindsay 1. This isn't just another group of stars, it's an ancient relic hurtling through space at speeds that defy logic, as if it were thrown from the hands of some unseen celestial force. Most star clusters move in predictable orbits, bound to their parent galaxies by gravity's unbreakable chains. But Lindsay 1, it's a rebel. Clocked at nearly 600,000 miles per hour, this cluster is moving so fast it could cross the distance between Earth and the Moon in just 20 minutes. That kind of speed doesn't happen by accident. What's even stranger is where this cluster came from. Lindsay 1 is old, unfathomably old. Its stars formed over 10 billion years ago, making them some of the most ancient objects in the Small Magellanic Cloud. But here's the twist: chemically, they don't quite match their surroundings. The cluster's metallicity, the amount of heavier elements mixed into its stars, is oddly high for such an early formation. That's like finding a medieval sword made of stainless steel. It shouldn't exist in that era. This mismatch suggests Lindsay 1 might not even belong here. Some astronomers think it was ripped from another galaxy entirely, catapulted into the Small Magellanic Cloud during a brutal collision billions of years ago. The physics behind such an ejection are mind-bending. To fling an entire star cluster across intergalactic space would require forces beyond comprehension, perhaps a close encounter with a supermassive black hole or a cataclysmic merger between galaxies. Yet Lindsay 1 isn't just surviving this journey, it's thriving. Despite its age and violent history, the cluster remains tightly bound, its stars resisting the tidal forces that should have torn them apart. That resilience raises even more questions. Are there invisible strands of dark matter holding it together? Or does its very existence hint at gaps in our understanding of gravity itself? Every detail about Lindsay 1 feels like a challenge to the textbooks. Its speed, its origins, even its survival, none of it fits neatly into our models. And that's what makes it so thrilling. This runaway cluster isn't just a curiosity, it's a cosmic mystery begging to be solved. If we can unravel its secrets, we might just rewrite the story of how galaxies evolve and how the universe flings its oldest treasures across the void. Among the ghostly remnants of exploded stars in the Small Magellanic Cloud, none are quite as puzzling as 1E0102.27219, a supernova remnant that refuses to follow the rules. Unlike the usual spherical shells left behind by stellar explosions, this one sprawls across space in a lopsided, chaotic sprawl, like a firework that burst unevenly. Its jagged edges and twisted tendrils of gas suggest a violent, asymmetrical death, one that challenges our understanding of how massive stars meet their end. But the real shocker, this cosmic wreckage is drenched in oxygen. Not just trace amounts, either vast clouds of it, enough to fill entire solar systems, glowing eerily against the darkness. Oxygen is normally forged deep in a star's core, then scattered by supernova, but here it's the dominant element, as if the dying star turned itself inside out before detonating. Where's the neutron star, though? That's the burning question. When a massive star collapses, the core should crush down into an ultra-dense neutron star or even a black hole, a cosmic tombstone marking the explosion's epicenter. But scans of 1E0102.27219 show nothing. No pulsing beacon of radiation, no telltale gravitational wobbles, just silence. Some theories suggest the neutron star might have been kicked away at incredible speeds during the blast, flung into the void like a cosmic bullet. Others wonder if it collapsed straight into a black hole without a trace. Either way, its absence is a gaping hole in the story, one that forces us to rethink how supernovae distribute their energy. Zooming in on the remnant's expansion over time reveals even more strangeness. Instead of ballooning outward evenly, its debris races outward in clumps and jets, as if the original explosion was more of a stutter than a bang. This isn't just artistic chaos, it's evidence that the star may have spun wildly before dying, or that hidden magnetic fields twisted the explosion into these bizarre shapes. Every new observation peels back another layer of mystery, leaving astronomers with more questions than answers. What makes this remnant truly special, though, is its rarity. Oxygen-rich supernova remnants are already uncommon, but one this lopsided and neutron star-less, it might be one of a kind. Studying it is like examining the fingerprints of a stellar catastrophe, a chance to decode exactly how certain stars tear themselves apart. And in a galaxy as chemically primitive as the Small Magellanic Cloud, where heavy elements are scarce, this oxygen-rich wreck could hold clues about how the building blocks of life spread through the early universe. So while it might look like just another cloud of debris, 1E0102.27219 is really a time capsule, one that's still teaching us how stars live, die, and shape the cosmos around them. Deep within the Small Magellanic Cloud, two cosmic oddities engage in a gravitational tango so extreme it bends the fabric of space itself, SMC X-1 and SMC X-3. These aren't just ordinary black hole candidates, they're X-ray binaries locked in deadly embraces with companion stars, wringing out energy in violent bursts that flicker like cosmic strobe lights. What makes them truly bizarre is how differently they behave, even though they share the same small corner of the universe. SMC X-1 pulses with eerie regularity, its X-ray flares rising and falling like clockwork every 7 days. Meanwhile, SMC X-3 is the wild child, unpredictable, flaring up without warning, then vanishing into near darkness for months. Astronomers have spent decades trying to decode why two objects so similar in theory could act so radically different in reality. The secret lies in their chaotic dance. Both systems consist of a black hole, or possibly an ultra-dense neutron star siphoning material from a neighboring star. As gas spirals toward the abyss, it heats up to millions of degrees, blasting out X-rays visible across intergalactic space. But here's where things get weird. SMC X-1's regular pulses suggest its accretion disk, the swirling ring of doomed matter, is stable, almost orderly. SMC X-3, by contrast, behaves like a broken faucet, its disk flickering between gushing and trickling. Some researchers think magnetic fields might be choking the flow sporadically, while others speculate the companion star itself is wobbling, disrupting the steady stream. Then there's the space-time warping. Every rotation of these black holes drags the very fabric of the universe along with them, an effect called frame dragging. Near SMC X-1, this distortion is so intense that light itself gets twisted into spirals as it struggles to escape. The system acts like a cosmic lighthouse, its beams bending unnaturally before reaching our telescopes. SMC X-3's warping is harder to map. Its erratic flares might be glimpses of matter briefly escaping the black hole's grip before vanishing forever. What really stumps scientists is the sheer intensity of their X-ray output. Both objects shine hundreds of times brighter than typical galactic black holes, as if they're overclocked versions of themselves. The Small Magellanic Cloud's low metal content might be the culprit. With fewer heavy elements, their companion stars burn hotter and shed material more violently, feeding the black hole's insatiable appetites. Yet for all their differences, these twins share one haunting trait. They're testing the limits of physics. Every flicker, every flare forces us to reconsider how black holes interact with their cosmic neighbors. Are they truly black holes or something even stranger? The answer might rewrite our understanding of how these gravitational monsters shape the galaxies they call home. The Small Magellanic Cloud holds a cosmic paradox, a structure so delicate it looks painted onto the void, yet so violent it reshapes the galaxy around it. Meet DEM L50, nicknamed the Blue Smudge by astronomers, a shimmering bubble of ionized gas stretching over 150 light-years, glowing with an eerie cerulean hue that defies expectations. Most nebulae radiate reds and pinks from hydrogen, but this one burns blue like a celestial welder's torch, a visual clue to the chaos within. Peer through Hubble's lens and the reason becomes clear. DEM L50 isn't just a gas cloud. It's a cosmic demolition site, sculpted by the hurricane-force winds of massive stars tearing through space at over 5 million miles per hour. At its heart lies a cluster of young, unstable stars, each one a volatile powerhouse. Their ultraviolet radiation ionizes the surrounding gas, stripping electrons from atoms and forcing them to emit that signature blue glow. But the real spectacle comes from their stellar winds, high-speed particles streaming outward like interstellar hurricanes. When these winds collide with slower-moving gas, they create shockwaves visible in Hubble's images as rippling, filamentous edges, like lace unraveling at the speed of light. The entire structure pulses with energy, expanding outward as if the bubble might pop at any moment. What's truly baffling is how pristine DEM L50 appears. Most structures this large get distorted by surrounding gas clouds or neighboring star clusters, yet this one floats in eerie isolation, its spherical form nearly perfect. Some researchers suggest it's a relic of a superbubble, a vast cavity carved by multiple supernova, whose shockwaves merged into a single, smooth shell. Others propose something stranger, that DEM L50 might be the aftermath of a runaway star collision, where two massive stars spiraled together before one erupted, leaving behind a shockingly symmetrical blast zone. Then there's the blue itself. That unnatural shade comes from doubly ionized oxygen, a rare sight in the metal-poor Small Magellanic Cloud. Normally, such heavy elements sink into a star's core, but here they've been blasted into space like confetti, suggesting the progenitor stars died unusually violent deaths. Every wavelength of light tells a different story. X-rays reveal searing hot gas at the bubble's edges, while infrared uncovers cooler dust drifting inward, possibly the seeds of future stars. DEM L50 is more than a pretty cosmic oddity. It's a laboratory for extreme physics. Its existence challenges assumptions about how interstellar environments evolve, proving even a tiny galaxy can produce structures rivaling those in far larger ones. And as the bubble continues to expand, it's writing its own epitaph one day. Those glowing blue tendrils will disperse, seeding the galaxy with the very elements needed for new stars, planets, and perhaps even life. For now, it remains a masterpiece of destruction and beauty, a reminder that even in the void, violence can create art. Lurking in the void between stars, untethered to any sun, drifts one of the Small Magellanic Cloud's greatest nomads, Ogle 2013 SMC X-1 This isn't just another frozen world, it's a cosmic castaway hurled from its birthplace into the infinite darkness, destined to wander forever. Astronomers call it a rogue planet candidate, but that clinical label barely captures its strangeness. Most planets orbit stars like obedient children, basking in their warmth. This one, it's utterly alone, adrift in the interstellar abyss with no sunlight to warm its frozen surface, no dawn or dusk, just endless night. We only know it exists thanks to a cosmic fluke, microlensing, a rare phenomenon where the planet's gravity briefly bent the light of a distant star like a magnifying glass. For a fleeting moment in 2013, as it drifted silently through the Small Magellanic Cloud, its presence warped spacetime just enough to betray its location. That tiny flicker, caught by the optical gravitational lensing experiment Ogle for short, revealed a world roughly the mass of Jupiter, untethered and invisible under normal circumstances. But here's the twist: rogue planets shouldn't be this common. Yet Ogle 2013 SMC X-1 is just one of many free-floating worlds discovered in this tiny galaxy, hinting at a hidden population of orphans drifting unseen. What could have sent it into exile? The leading theory is brutal yet elegant gravitational chaos. In crowded star systems, young planets often jostle for position, locked in violent tug-of-wars with siblings or passing stars. One wrong interaction, one too close encounter with a massive neighbor, and snap, a planet goes careening into the void like a ball released from a slingshot. Argyle 2013 SMC X-1 might have been launched by its own sun, or perhaps a close brush with a wandering star ripped it from its orbit. Either way, its fate was sealed, a lifetime of wandering through temperatures barely above absolute zero. Imagine its surface, without a star to warm it. The planet's atmosphere, if it ever had one, has long since frozen into a glacial crust, a wasteland of nitrogen ice and solidified gases. Any traces of water would exist as rock-hard glaciers, colder than Pluto's heart. And yet, beneath that icy shell, something tantalizing might lurk. Rogue planets could theoretically harbor deep, hidden oceans kept liquid by geothermal heat or tidal forces, sandwiched between layers of ice and rock. It's a long shot, but if life could exist anywhere in the darkness, it might be here, clinging to hydrothermal vents in perpetual midnight. What makes this rogue so fascinating isn't just its loneliness, it's what it represents. For every Argyle 2013 SMC X-1 we detect, there could be thousands more invisible to our telescopes. These cosmic nomads might outnumber stars in the galaxy, a shadow population of worlds uncharted and unnamed. Some could even be interstellar arcs carrying frozen remnants of life across the void between stars. The discovery challenges our very definition of a planet, blurring the line between world and wanderer. And then there's the bigger question: how many more are out there, drifting unseen? The Small Magellanic Cloud, with its sparse stars and low metal content, shouldn't be an ideal breeding ground for planets, let alone rogue ones. Yet here they are, defying expectations. Every microlensing event is a fleeting glimpse into this hidden diaspora, a reminder that the universe is far stranger and far more restless than we ever imagined. Argyle 2013 SMC X-1 isn't just a scientific curiosity. It's a ghost story written in gravity, a single verse in an epic poem of celestial exile. And somewhere out there, in the endless dark, it's still traveling, carrying its secrets into the unknown. In the cosmic ballet of the Small Magellanic Cloud, one performer stands out for its sheer precision and violent grace: pulsar J0045-7319. This isn't just any pulsar, it's a celestial metronome locked in a gravitational tango with a massive companion star, spinning so fast it distorts the very fabric of space around it. Imagine a neutron star, a dense remnant of a supernova packing more mass than our sun into a sphere the size of a city, rotating hundreds of times per second. Now picture it whirling around another star 20 times heavier than our sun, their orbits so tight they could fit inside Mercury's path. The result: a dance so extreme it defies intuition, where time itself slows and speeds up like a broken clock under the pulsar's gravitational spell. What makes this system truly bizarre is the pulsar's spin. Most neutron stars rotate steadily, but pulsar J0045-7319 is a relativistic marvel, its axis wobbling like a top about to fall, a phenomenon called precession. Every rotation, its beams of radiation sweep across Earth with clockwork precision, allowing astronomers to track its every stumble. This isn't just a quirk, it's a golden opportunity. By measuring the pulsar's tiny wobbles, scientists can map the gravitational warping caused by its companion star, testing Einstein's theory of general relativity in ways no laboratory on Earth ever could. Then there's the orbit, a cosmic carousel ride where the rules of physics get stretched to the limit. Every 43 days, the pulsar plunges dangerously close to its companion, skimming through the star's outer atmosphere like a stone skipping across a lake. The friction should slow it down, but pulsar J0045-7319 somehow maintains its blistering speed, as if fueled by some unseen force. Some researchers suspect the star's intense magnetic field is acting like an invisible shield, redirecting the pulsar's path. Others wonder if the system is leaking gravitational waves, ripples in space-time predicted by Einstein but fiendishly difficult to detect. If confirmed, these waves would carry secrets about how matter behaves under extreme conditions, clues to the universe's most hidden forces. The precision of this system is almost eerie. Pulsars are nature's most accurate clocks, their beams arriving with nanosecond consistency over decades. But pulsar J0045-7319 takes it further. Its pulses arrive so predictably that astronomers can detect minute delays caused by its companion's gravity, bending the path of light, an effect so subtle it's like hearing a whisper in a hurricane. This level of precision turns the pulsar into a cosmic laboratory where even the tiniest deviation could reveal new physics. What's next for this cosmic duo? The companion star, massive and unstable, won't live forever. When it explodes, and it will, the pulsar might be catapulted into space, or the explosion could trigger an even tighter bond. For now, their dance continues, a fleeting spectacle of gravity and light, a reminder that even in the vastness of space, the most extraordinary discoveries often come in pairs. Among the swirling chaos of the Small Magellanic Cloud, two galaxies perform a slow-motion dance of destruction and creation, NGC 465 and NGC 460, nicknamed the taffy galaxies for the way their stretched arms resemble pulled candy. These aren't serene island universes spinning in isolation. They're caught in a gravitational tug-of-war so intense it's warping them into surreal shapes, stretching their stars and gas into luminous bridges that glow with newborn suns. The collision has turned them into a single, tangled spectacle, a cosmic car crash unfolding over millions of years. Look closely and the violence becomes breathtaking. The galaxy's spiral arms, once neat, symmetrical pinwheels, now trail behind them like celestial streamers, ripped outward by tidal forces. Between them, a shimmering bridge of gas and dust spans the void, a highway of star formation lit up by clusters so young they're practically stellar infants. This isn't just random debris, it's a stellar nursery forged from chaos, where the collision's shockwaves compressed gas clouds until they ignited into stars. Normally, galaxies this small wouldn't produce such prolific bursts of starbirth, but the taffy pair defies expectations, turning destruction into creation. Simulations reveal where this dance is headed. Over the next few 100 million years, the galaxies will spiral closer, their cores drawn together by gravity's inexorable pull. Eventually, they'll merge into a single, misshapen galaxy, one that might resemble a football or a bloated ellipsoid, its original structures erased forever. But the aftermath could be even more fascinating. Mergers like this often trigger quasar-like activity, as supermassive black holes at their centers awaken and feast on the swirling gas. Or if the collision is just slightly off-kilter, they might leave behind a lopsided wreck, a galactic oddball drifting through the Small Magellanic Cloud for eons. What makes these two so special isn't just their fate, it's their rarity. The Small Magellanic Cloud, already a dwarf galaxy, isn't known for hosting many interacting pairs. Yet here they are, locked in an embrace that's reshaping them on a fundamental level. Their stretched arms and star-forming bridges offer a snapshot of a process that shaped much larger galaxies, including our own Milky Way, billions of years ago. They're a living fossil of the universe's violent adolescence, a reminder that even in the quiet corners of space, chaos and creation go hand in hand. For now, the taffy galaxies remain a spectacle in progress, a slow-motion collision we're lucky enough to witness. Every telescope pointed their way captures a different chapter in their story, one that's still being written, one gravitational twist at a time. Hidden in the heart of the Small Magellanic Cloud, there's a shadow so thick it swallows starlight whole. BHR 71, a dark globule that stands like a cosmic ink blot against the galaxy's glow. Unlike the vibrant nebulae and star clusters around it, this dense cloud of gas and dust is eerily opaque, a void where the universe seems to hold its breath. If you could fly through it, you'd find yourself in utter darkness, surrounded by particles so fine and tightly packed they blot out even the brightest neighboring stars. It's not just absence, it's a presence, a tangible thing with weight and intent, as if the cosmos itself carved out a pocket of nothingness and dared light to trespass. But this isn't just emptiness. BHR 71 is a cocoon, a stellar nursery in the making. Deep within its frigid heart, gravity is quietly at work, pulling molecules together so slowly it would take human lifetimes to notice. Given enough time, millions of years, perhaps those whispers of attraction will crescendo into a roar, collapsing the cloud's core until it ignites into new stars. Right now, though, it's all potential, a frozen tableau of creation waiting to unfold. That's the paradox of dark globules. They're both endings and beginnings, the ashes of dead stars and the seeds of new ones. What makes BHR 71 especially haunting is how it defies its surroundings. Around it, the Small Magellanic Cloud sparkles with star-forming regions like NGC 346, where gas glows pink and blue under the assault of young, violent stars. Yet here, just a cosmic stone's throw away, BHR 71 sits in stark silence, absorbing light instead of radiating it. The contrast couldn't be sharper, like finding a cave behind a waterfall, a place where the universe's usual rules don't apply. Scientists study globules like this precisely because of their stubborn opacity. The dust here is so thick it blocks visible light, but astronomers have tricks to peer inside. Infrared telescopes, which see heat rather than light, reveal faint warmth deep in the cloud's core, hints of future stars taking shape. Radio waves, unbothered by the dust, map the globule's intricate magnetic fields, which sculpt the collapsing gas into delicate filaments. Even the silence speaks. The absence of certain molecules suggests the cloud's interior is colder than the void between galaxies, a chill so profound it slows chemistry itself. And then there's the mystery of its birth. How does something so dense form in a galaxy as sparse as the Small Magellanic Cloud? Most theories point to shockwaves, perhaps from a nearby supernova, that compressed loose gas into this tight, dark knot. Others wonder if BHR 71 is a fossil, a relic from a time when the dwarf galaxy was richer in dust and heavier elements. Whatever the truth, its existence challenges assumptions about how stars form in such metal-poor environments. For now, BHR 71 remains a silhouette, a cutout in the cosmic canvas. But someday, those shadows will blaze with light, and this silent sentinel will join the very spectacle it once defied. Until then, it's a reminder that even in the brightest corners of the universe, darkness holds its own secrets and its own kind of beauty. Somewhere in the vast expanse of the Small Magellanic Cloud, a star is making a break for it, hurtling through space so fast it's essentially giving its home galaxy the cosmic finger. Meet J01020100-71222208, a hypervelocity rogue on a one-way trip to intergalactic space. Clocked at over 900,000 miles per hour, this stellar fugitive isn't just moving quickly, it's practically teleporting compared to most stars, crossing the equivalent of Earth to the Moon in under 30 minutes. At this rate, it'll escape the Small Magellanic Cloud entirely in a few million years, becoming a lone wanderer in the abyss between galaxies. How does a star reach such blistering speeds? The answer lies in cosmic violence of the highest order. Most astronomers agree J01020100-71222208 was once part of a binary system, orbiting another star in a delicate gravitational dance. Then disaster struck. Its companion likely went supernova, exploding with such force that the sudden loss of mass sent this star careening outward like a slingshot released at light speed. Imagine standing on a merry-go-round when someone suddenly cuts the chain. That's essentially what happened here, except with forces so extreme they'd shred any matter foolish enough to stand in the way. Tracking its trajectory reveals even more intrigue. Unlike most hypervelocity stars that streak outward in straight lines, this one follows a slight curve, suggesting it might have gotten an extra gravitational kick from passing near dense objects like black holes or massive star clusters. It's leaving behind a wake of ionized gas, a glowing trail that acts like breadcrumbs back to its point of origin. Follow that path, and you'll find a region littered with supernova remnants, the graveyard where its explosive escape likely began. What's truly humbling is the star's composition. Spectroscopy shows it's rich in heavy elements: oxygen, neon, even traces of silicon, materials typically forged in the hearts of massive stars and scattered by supernova. That's another clue pointing to its violent past. This isn't just any runaway star, but one that's essentially covered in the ashes of its former companion, wearing the remnants of that cataclysm like cosmic tattoos. And then there's the future, with no gravity strong enough to reel it back in. J01020100-71222208 will keep accelerating, propelled by the galaxy's rotation until it's flung into the void. In a billion years, it might be the coldest, loneliest star in existence, a frozen relic drifting through the emptiness between galaxies, its light too faint for any civilization to notice. Until then, it serves as a reminder, even in a universe bound by gravity's rules, there's always an exception, a rebel that breaks free and never looks back. Among the tangled stellar nurseries of the Small Magellanic Cloud, one nebula glows with the eerie radiance of a blood moon, N76, nicknamed the Crimson Eye. Unlike the typical pastel pinks of hydrogen-rich nebulae, this cosmic cloud burns a deep, unsettling red, as if the fabric of space itself has been wounded. The color comes from an anomaly in its ionization. While most emission nebulae get their glow from ultraviolet radiation stripping electrons off hydrogen atoms, N76's crimson hue suggests something far stranger at play. Here, the gas isn't just ionized, it's overcooked, bombarded by energies so intense they excite hydrogen to emit light at wavelengths rarely seen in nature. At the heart of this scarlet spectacle sits a star so peculiar it's redefining what we know about stellar evolution. Designated WR124, the central engine of N76 isn't the steady, stable furnace we'd expect. Instead, it's a Wolf-Rayet star, a volatile, short-lived beast expelling its own atmosphere at speeds exceeding 3 million miles per hour. Peer at its spectrum, and the data looks chaotic: wild emission lines of helium and nitrogen, bizarre gaps where hydrogen should be, and an energy output flickering like a faulty light bulb. This star isn't just aging, it's unraveling, shedding layers so violently they form concentric shockwaves in the surrounding nebula. The Crimson Eye's structure adds another layer of intrigue. Most nebulae around Wolf-Rayet stars form symmetric bubbles or claw-like tendrils, but N76 sprawls unevenly, its edges frayed like torn fabric. Radio telescopes reveal why. The nebula is colliding with an invisible wall of colder molecular gas, compressing its eastern flank into a glowing arc while leaving the western side diffuse and ghostly. This collision zone acts like a cosmic petri dish, triggering pockets of star formation along the shock boundary, stellar infants born from the violence of their predecessors' death throes. Then there's the mystery of its nickname's origin. Early astronomers peering through early 20th century telescopes described N76's appearance as a lidless eye staring from the depths of space. Modern imagery confirms the unsettling resemblance. The central star's intense winds have carved a tunnel through the nebula's core, creating a pupil-like void surrounded by veiny filaments of gas. When viewed edge-on, the effect is uncanny, a colossal, unblinking eye suspended in the void, its crimson iris flickering with the light of dying stars. What makes the Crimson Eye truly unique is its defiance of the Small Magellanic Cloud's typical chemistry. This dwarf galaxy's low metal content usually prevents the formation of such massive, unstable Wolf-Rayet stars, yet here one blazes defiantly, proving nature's rulebook still has pages left unread. Every observation raises new questions. Why hasn't the star's ferocious wind shredded the nebula entirely? How did it retain enough hydrogen to create such an ionization masterpiece? The answers might rewrite our understanding of how stars live and die in metal-poor galaxies, and why some choose to go out in a blaze of crimson glory. Tucked away in the outskirts of the Small Magellanic Cloud, there's a celestial time capsule so ancient it predates most of the galaxy around it, NGC 121, a globular cluster that astronomers call the fossil. Unlike the vibrant, star-studded clusters scattered throughout the cosmos, this one feels frozen in time, a relic of the universe's infancy when galaxies were just taking shape. Its stars formed over 10 billion years ago, making NGC 121 one of the oldest known structures in its dwarf galaxy, a living snapshot of conditions just a few billion years after the Big Bang. What's striking about this cluster isn't just its age, it's the eerie absence of youth. While most globular clusters in the Milky Way show at least some signs of later star formation, NGC 121 is a monolith of uniformity, its stellar population eerily homogeneous. Every star here is ancient, metal-poor, and practically identical in composition, as if the cluster slammed the door on new star birth the moment it formed. That purity makes it a rarity even among fossils. It's essentially a closed ecosystem, a stellar retirement home where nothing new has happened for eons. Compare it to clusters like Omega Centauri in our own galaxy, and the differences leap out. Milky Way globulars often have complex chemical fingerprints, with multiple generations of stars hinting at messy, prolonged formation. NGC 121, by contrast, is a one-and-done phenomenon, its stars all forged in a single, frenzied burst of creation before the cluster went dormant. That simplicity is a clue to its origins. The Small Magellanic Cloud's sparse gas reserves back then meant star formation was a fleeting event, leaving clusters like this one as solitary remnants of a more chaotic era. Yet the real mystery is how it survived at all. Globular clusters are notoriously fragile, vulnerable to gravitational disruptions from passing galaxies or internal dynamics tearing them apart. The fact that NGC 121 still holds itself together, its stars bound in a tight spherical embrace despite billions of years of cosmic turbulence, suggests it's denser, or perhaps more massive than we can measure. Some theorists speculate it might harbor an unseen cache of dark matter at its core, an invisible anchor keeping it intact. Others wonder if it's just lucky, having drifted through quieter regions of the dwarf galaxy while younger clusters were shredded. Studying NGC 121 is like dusting off a prehistoric artifact. Its stars preserve the chemical makeup of the early universe, untouched by the heavier elements later generations would create. That makes it a benchmark for understanding how galaxies assemble over time, and a stark reminder that some corners of the cosmos refuse to move on. While the Small Magellanic Cloud around it churns with new stars and colliding gas clouds, this ancient cluster lingers, a silent witness to the universe's first act. It's not just a relic, it's a challenge, daring us to unravel how something so old could endure in a galaxy so young. Somewhere in the depths of the Small Magellanic Cloud, an invisible force sculpts the cosmos with silent shockwaves. SNR 0103-72.6, a supernova remnant so perfectly ring-shaped it looks like a smoke ring blown into space. But this isn't just debris from an ancient explosion. It's a radio powerhouse pulsing with emissions so intense they drown out nearly everything else in its vicinity. Tune a telescope to the right frequency, and the loop blazes to life, a neon sign in the void advertising violence from long ago. What's strange is how crisp the ring appears. Most supernova remnants spread unevenly, their shockwaves warped by interstellar gas or their own turbulent histories. But SNR 0103-72.6 is almost geometric, its circular form so precise it could have been drawn with cosmic compasses. The secret lies in its environment. This remnant is expanding into a near-perfect vacuum, a region of the Small Magellanic Cloud so sparsely populated that nothing distorts its outward rush. The result, shockwaves that propagate symmetrically, creating this rare, textbook-perfect loop. Then there's the radio roar. Unlike optical images, which show only faint filaments of glowing gas, radio telescopes reveal a structure crackling with synchrotron radiation, high-energy electrons spiraling around magnetic fields at nearly light speed. These emissions aren't just remnants of the explosion. They're continuously generated proof that the shockwave is still accelerating particles even centuries later. Somewhere along that glowing rim, invisible cosmic slingshots are flinging electrons to energies that dwarf anything humanity's particle colliders can produce. Debates rage about what kind of star birthed this phenomenon. The remnant's chemical fingerprints suggest a Type 1, a supernova, the thermonuclear detonation of a white dwarf star. But there's a problem. The loop's expansion speed is slower than most Type 1 remnants, hinting it might instead be the corpse of a massive star that collapsed inward before rebounding outward. Could it be a rare hybrid, a white dwarf that stole too much mass from a companion, or a massive star that died unusually quietly? Overlaying radio and optical images only deepens the mystery. The visible light shows delicate ribbons of oxygen and sulfur-cooler debris from the star's outer layers, while the radio paints the violent frontier where the shockwave meets interstellar space. Together, they form a haunting composite. The ghost of the star's death throws wrapped in an invisible fist of energy. What's clear is that SNR 0103-72.6 isn't done teaching us. Every frequency it emits carries clues about how stars die, how shockwaves shape galaxies, and how the universe recycles its most violent moments into something strangely beautiful. In the end, this loop isn't just a relic, it's a classroom, and its lessons are written in light, radio waves, and the echoes of an explosion we'll never see. Some stars don't just share the sky, they're locked in an embrace so tight, they begin to warp reality itself. Meet AB8 and AV304, two binary systems in the Small Magellanic Cloud where the stars don't just orbit, they dance. These aren't your typical stellar pairs lazily circling one another at a safe distance. These are cosmic tango partners, so close they could fit inside our solar system, their surfaces stretched and distorted by gravitational forces beyond imagination. Take AB8 first, a pair of stars so tightly bound they complete an orbit in less than 2 days. The primary star is a blazing O-type giant, 20 times more massive than our Sun, while its companion is a smaller but no less intense Wolf-Rayet star, shedding its own atmosphere at breakneck speeds. Their proximity creates a gravitational tug of war that reshapes both stars into teardrops, their atmospheres stretched toward each other like celestial taffy. Matter streams between them in a glowing bridge, a river of superheated gas that flickers with X-ray flares as it crashes onto the Wolf-Rayet star's surface. Then there's AV304, a system that turns stellar synchronization into an art form. Here, two massive B-type stars whirl around each other so precisely their rotation is tidally locked. Each star always shows the same face to its partner, like the moon does to Earth. But the real spectacle happens when they flare. Every few orbits, magnetic fields between the stars snap and reconnect, unleashing bursts of energy so violent they outshine the entire system for hours. These aren't just random eruptions, they're clockwork tied to the star's orbital rhythm like a cosmic heartbeat. What makes these binaries truly bizarre is how they challenge our models of stellar evolution. Normally, stars this massive and close would have merged or torn each other apart eons ago. Yet here they are, persisting in a delicate gravitational balance, as if the universe itself paused to admire their choreography. Their light curves graphs of their brightness over time look less like smooth waves and more like jagged mountain ranges, riddled with dips and spikes as eclipses, flares, and tidal distortions play out in real time. The dance isn't eternal, though. Both systems are racing toward explosive futures. AB8's Wolf-Rayet star is shedding mass so rapidly it'll likely collapse into a supernova within a few 100,000 years, possibly triggering its partner's destruction in a chain reaction. AV304's stars, meanwhile, are spiraling inward, destined to either merge into a single, even more massive star or detonate in a pair of supernova that'll leave behind a binary black hole. For now, though, they're a fleeting masterpiece, proof that even in the vastness of space, the most beautiful things often come in pairs. In the heart of the Small Magellanic Cloud, a cosmic tempest rages, N66, the Witch's Broom Nebula, where jagged filaments of gas slice through space like streaks of lightning frozen in time. This isn't just debris from a stellar explosion. It's a relic of violence so intense it sculpted the surrounding gas into eerie, organic shapes. Viewed through narrowband filters, the nebula transforms into a spectral masterpiece, its tendrils glowing with an otherworldly green hue, a signature of doubly ionized oxygen, energized to frequencies rarely seen in the cosmos. The color gives the structure an almost supernatural aura, as if lit by some cosmic witchlight casting shadows across the surrounding starfield. The broom's filaments tell a story of destruction on an unimaginable scale. Each twisted strand is a shockwave fossil, a ripple from a supernova that tore through the interstellar medium at millions of miles per hour. As the blast wave plowed into surrounding gas, it compressed and heated the material, leaving behind these intricate branching patterns. Some filaments stretch over 50 light-years longer than the distance between our Sun and its nearest stellar neighbors, yet they're so delicate that gravity hasn't yet pulled them apart. It's a fleeting spectacle, a snapshot of chaos caught mid-decay. What makes N66 truly mesmerizing is how it plays with light. Under hydrogen alpha filters, the nebula blazes crimson, its tendrils thick and rope-like. Switch to an oxygen 3 filter, and the scene shifts dramatically. The green hues dominate, revealing structures within structures, like veins in a celestial leaf. This chromatic duality isn't just artistic, it's scientific gold. The varying colors map different temperatures and densities, helping astronomers reconstruct the supernova's energy distribution. The green zones, for instance, mark where the shockwave was most efficient at stripping electrons from oxygen atoms, leaving them to glow with an almost radioactive intensity. For amateur astronomers hoping to catch a glimpse, the Witch's Broom offers both challenge and reward. A modest telescope under dark skies can reveal its faint smudge, but to truly appreciate its details, narrowband filters are essential. A nebula filter like an O3 or UHC will amplify the contrast, making the filaments pop against the blackness of space. The best views come from long-exposure astrophotography, where stacked images tease out the delicate interplay of colors and textures. Timing matters too. Observing during the Small Magellanic Cloud's highest elevation minimizes atmospheric interference, sharpening those elusive green tones. Yet, even through the finest telescopes, N66 keeps its secrets. Why do some filaments glow greener than others? What caused the supernova's shockwaves to branch so asymmetrically? Every observation peels back another layer, reminding us that the universe's most haunting beauty often lies in its ruins, and that even a witch's broom swept across the cosmos can leave trails of wonder in its wake. Drifting through the outskirts of the Small Magellanic Cloud like a phantom, there's an invisible structure that defies everything we know about cosmic motion, HVC 306-2+230. At first glance, this high-velocity cloud seems unremarkable, just another wisp of hydrogen gas floating in the void. But look closer and the numbers don't add up. This cloud is racing through space at nearly 250 kilometers per second, far faster than the gravity of visible matter should allow. It's as if something unseen is tugging at it, a cosmic puppeteer yanking its strings with irresistible force. That puppeteer, many astronomers whisper one answer: dark matter. What makes this cloud so puzzling isn't just its speed, it's the fact that it shouldn't exist at all in its current form. Intergalactic gas clouds like this are typically shredded apart by tidal forces or evaporated by ultraviolet radiation from nearby galaxies. Yet HVC 306-2+230 has held itself together for billions of years, a cohesive structure barreling through space with eerie resilience. The math suggests it's surrounded by a hidden halo of mass, an invisible scaffold of dark matter keeping it intact against all odds. If true, this could be one of the clearest examples of a dark galaxy, a clump of dark matter with just a wisp of ordinary matter clinging to it, a ghostly echo of a galaxy that never fully formed. Detecting something so elusive requires clever tricks. The cloud itself emits no light, but its hydrogen atoms occasionally absorb specific wavelengths from distant quasars passing behind it. Like a cosmic fingerprint, these absorption lines reveal the cloud's composition, velocity, and even its rough shape. Radio telescopes, tuned to the faint hum of neutral hydrogen, map its contours in painstaking detail, tracing outlines of a structure that shouldn't be there. Each observation deepens the mystery. The cloud's motion suggests it's not just passing through the Small Magellanic Cloud. It might be orbiting it, held in place by an unseen gravitational anchor. The implications ripple far beyond this single cloud. If HVC 306-2+230 truly is wrapped in dark matter, it could rewrite our understanding of how dwarf galaxies form. Current theories suggest the Small Magellanic Cloud and other satellite galaxies are embedded in vast halos of dark matter, but finding direct proof has been fiendishly difficult. Here, in this invisible, fast-moving cloud, we might have a smoking gun, a dark matter clump caught in the act of shepherding ordinary matter through the cosmos. It's a clue that could bridge the gap between theoretical models and the messy reality of galactic evolution. Yet the cloud refuses to give up its secrets easily. Some researchers argue its strange motion could come from a past collision with another gas cloud, or perhaps an ancient interaction with the Large Magellanic Cloud. Others point to magnetic fields threading through intergalactic space, invisible forces that might steer gas in unexpected ways. But the dark matter explanation lingers, tantalizing and unresolved, a reminder that the universe's greatest mysteries often hide in plain sight, or in this case, in the absence of it. For now, HVC 306-2+230 remains a cosmic cipher, a whisper of something vast and unseen moving through the darkness. Every scan, every spectrum brings us closer to decoding its truth. And when we do, we might just find that the real story isn't about the cloud at all, but about the invisible hand guiding it, a shadowy force sculpting the cosmos in ways we're only beginning to imagine. Deep in the Small Magellanic Cloud, a cosmic fraudster keeps pulling off the universe's most brazen con, a 2E0101.5-7225, a white dwarf that refuses to die. Nicknamed the Zombie Star, this stellar remnant has cheated death not once, not twice, but multiple times, erupting in violent outbursts that should have torn it apart, only to somehow stitch itself back together like a cosmic phoenix. Most white dwarfs fade quietly into the void, but this one, it's still feeding, still exploding, still rewriting the rules of stellar demise. Here's the scam: this white dwarf isn't acting alone. It's locked in a parasitic dance with a companion star, siphoning hydrogen-rich material from its neighbor's atmosphere like a celestial vampire. Over time, the stolen gas piles onto the white dwarf's surface, compressing under unimaginable gravity until, boom, it detonates in a thermonuclear blast bright enough to outshine entire galaxies. These eruptions, called recurrent nova, should be rare, occurring maybe once every few 100,000 years. But 2E0101.5-7225 erupts every few decades, as regular as clockwork, each explosion violent enough to obliterate a planet, yet somehow leaving the white dwarf intact. What makes this star truly bizarre is how it survives these self-inflicted catastrophes. Normally, nova blow away the outer layers of accumulated material, resetting the countdown to the next explosion. But the zombie star is messier and greedier. Observations show it's holding onto a fraction of the stolen hydrogen each time, letting it rebuild its explosive fuel supply faster than physics should allow. It's like a gambler who keeps losing but always finds another chip to push onto the table. Then there's the X-ray betrayal. Between eruptions, this white dwarf doesn't cool off like it's supposed to. Instead, it keeps glowing fiercely in X-rays, a sign that fusion might still be smoldering under its surface, a stellar furnace that refuses to shut down. Some astronomers suspect its core is hotter or denser than typical white dwarfs, a quirk of its formation that lets it cheat the cosmic odds. But the biggest mystery isn't how it survives, it's how long this can last. Each explosion nudges the white dwarf closer to the ultimate limit, the Chandrasekhar mass, the point where gravity overwhelms all resistance, triggering a supernova that would vaporize it completely. Yet against all odds, 2E0101.5-7225 keeps towing that line without crossing it, a high-wire act with no net. Is it luck, a fluke of physics, or is there something darker at play, some unseen mechanism letting this star toy with forces that should have destroyed it eons ago? Every eruption is a reminder that the universe loves an outlaw, and this zombie might just outlive us all. There's a phantom lurking in the Small Magellanic Cloud that looks ripped straight from the Abyss DEM L51, a supernova remnant so eerily organic it's earned the nickname the cosmic jellyfish. Through the lens of multi-wavelength astronomy, this celestial wreckage transforms into something out of a deep-sea nightmare, its tendrils of glowing gas stretching over 150 light-years like venomous filaments drifting through the void. But this isn't just a pretty cosmic coincidence. Those delicate, looping structures are the scars of a stellar explosion so violent, it left behind not one but two distinct shockwaves, a rare double-layered relic of destruction. Peel back the layers and the science becomes even more mesmerizing. The outer shockwave, visible in X-rays as a blistering blue halo, marks the initial blast's edge, where the supernova's fury first slammed into interstellar gas at millions of miles per hour. Inside it, a second, slower shockwave glows crimson in optical light, a ghostly echo of the star's final collapse. Together, they create a nested structure like ripples from two stones thrown into a pond. But here's the twist, those ripples aren't just expanding, they're interacting, their collisions sculpting the jellyfish's tentacles into delicate, knotted braids. Hubble's visible light images catch these filaments in haunting detail, their oxygen-rich strands glowing greenish-blue, a signature of gas heated to searing temperatures, then left to cool into these eerie, undulating shapes. What really seals the deep-sea illusion are the clumps. Nestled along the tendrils are dense knots of gas and dust, cosmic stingers, where material has pooled under gravity's pull. These knots aren't static, they're turbulent, flickering with newly formed shock fronts as they plow through surrounding gas. Some even harbor baby stars, their faint glow detectable in infrared, as if the jellyfish is spawning new life amid its own ruin. It's a stunning paradox, destruction giving birth to creation, a cycle written in the very tendrils that make this remnant so haunting. Yet DEM L51's true brilliance lies in what it reveals about stellar deaths. Most supernova remnants fade into smooth shells or chaotic debris fields, but this one's delicate structure suggests its progenitor star exploded inside a pre-existing bubble of gas, likely carved by the star's own winds before its demise. That bubble acted like a sculpting tool, channeling the explosion's energy into these intricate patterns. It's a cosmic fingerprint, a clue that the star's final moments were shaped by its life's work. And then there's the jellyfish's silent testimony to the Small Magellanic Cloud's unique chemistry. Unlike remnants in our galaxy, DEM L51's filaments are strikingly metal-poor, a relic of the dwarf galaxy's primordial composition. Every glowing strand is a time capsule, preserving the raw ingredients of an earlier universe before generations of stars seeded space with heavier elements. So while it may resemble a creature from Earth's oceans, DEM L71 is anything but familiar. It's a celestial masterpiece, a reminder that the universe's most violent acts can leave behind beauty, and that sometimes to understand the cosmos, we need to look not just to the stars, but to the depths of our own planet for clues. Nestled in the heart of the Small Magellanic Cloud, there's a cosmic contradiction that's left astronomers scratching their heads. NGC 330, an open cluster that refuses to play by the rules. At first glance, it looks like any other sparkling gathering of stars, but peer closer, and the contradictions pile up. This cluster shouldn't exist in its current state, not with its bizarre blend of stellar grandparents and newborns, not with its dizzying spin, and certainly not with its stubborn refusal to settle on something as basic as its own distance from Earth. Take its age crisis first. Open clusters are usually stellar nurseries where stars are born from the same gas cloud around the same time, like siblings at a family reunion. But NGC 330 is more like a party crasher, a chaotic mix of ancient red giants and hot, young blue stars burning side by side. The red giants hint at an older population, perhaps 8 to 10 billion years old, while the blue stars scream youth, some barely a few million years into their existence. It's as if this cluster has been recycling its material for eons, birthing new stars long after its initial formation, a phenomenon rarely seen in such compact groups. Then there's the spin. Most open clusters drift lazily through space, their stars loosely bound by gravity, but NGC 330 whirls like a cosmic top, rotating so fast its outer stars risk flying into the void. This kind of motion is usually seen in globular clusters, dense, ancient balls of stars, not in the more fragile open variety. The cluster's rapid rotation suggests a violent past, possibly a close encounter with another cluster or a brush with a rogue gas cloud that set it spinning like a celestial dreidel. But the real enigma is its distance. Pinpointing how far away NGC 330 lies has sparked debates for decades. Some measurements place it squarely within the Small Magellanic Cloud, while others suggest it might be closer, floating in the foreground like a cosmic illusion. The uncertainty isn't just an academic quibble, it changes everything. If it's truly part of the Small Magellanic Cloud, its odd mix of stars becomes even more puzzling, given the dwarf galaxy's typically metal-poor environment. If it's closer, its properties might align better with Milky Way clusters, but then why does it look so much like a resident of its neighboring galaxy? Compare it to a textbook open cluster like the Pleiades, and the differences are stark. The Pleiades is a cohesive family of young stars, all shining with similar brilliance, all moving in harmony. NGC 330, by contrast, is a patchwork quilt stitched together from disparate pieces, its history written in conflicting stellar signatures. Some researchers argue it might be the result of a merger, two clusters colliding and blending their populations. Others speculate it's a rare second-generation cluster, where new stars formed from the ashes of older supernova within the same gravitational cradle. One thing's certain, NGC 330 challenges our assumptions about how stars live and gather. It's a reminder that even the most familiar cosmic structures can hide astonishing secrets, and that sometimes the most intriguing puzzles are the ones we thought we already understood. Every telescope pointed its way peels back another layer, revealing not just answers but new questions waiting in the starlight. On February 23, 1987, the night sky briefly hosted the brightest stellar explosion seen in nearly 4 centuries, supernova 1987A. For a few glorious months, this dying star outshone entire galaxies, casting its light across 160,000 light-years from the Large Magellanic Cloud to Earth. But here's where the story twists. While the supernova itself faded, its echo lingers in the Small Magellanic Cloud, a cosmic afterimage that refuses to disappear. Decades later, astronomers still watch in awe as light from that cataclysm continues to bounce off interstellar dust, illuminating hidden structures like a flashlight sweeping across a cavern. These aren't just faint glimmers, they're full-blown celestial revelations. The most stunning, a series of glowing rings, concentric shells of gas that erupted from the progenitor star long before its demise. When the supernova's light slammed into these pre-existing structures, it set them ablaze with an ethereal glow, revealing nested layers of stellar debris like tree rings marking a violent past. The innermost ring, a perfect hoop of hydrogen and helium, glows hot enough to fry a planet, while outer loops ripple outward with eerie symmetry, their fluorescence fading as they expand into the void. But the real magic lies in how these echoes evolve. Unlike the static snapshots of most astronomical phenomena, this one's a movie. Year after year, new patches of dust catch the supernova's ancient light, creating shifting patterns that let scientists reconstruct the explosion in 3 dimensions. By tracking these reflections, astronomers have mapped not just the debris field but the very shape of space around it. Some echoes even reveal gaps in the dust, tunnels carved by the star's own stellar winds before it died, now backlit by its final scream. Then there's the mystery of the missing compact remnant. Every core collapse supernova should leave behind either a neutron star or a black hole, but despite decades of searching, neither has been definitively spotted in supernova 1987A's wreckage. Some theorists argue it might be hiding behind thick dust, while others speculate the explosion was so asymmetrical it kicked the remnant clear out of the debris field. Recent X-ray and neutrino detections hint at something lurking in the chaos, but the question remains open, a tantalizing loose end in an otherwise textbook stellar death. What makes these echoes more than just pretty relics is their scientific payoff. By studying how light interacts with the ring's molecules, researchers have clocked the supernova's shock waves at over 20 million miles per hour, speeds that defy earlier models. The echoes also act as cosmic chemistry labs, showcasing how heavy elements forged in the explosion, like titanium, cobalt, and gold, mix with interstellar gas, seeding future generations of stars and planets. For amateur astronomers, tracking these echoes is the ultimate time capsule hunt. Though the rings require professional telescopes to resolve, their slow fade offers a unique chance to witness history in real time. Every photon we catch is a messenger from that fateful night in 1987, a whisper from a star that died before human civilization began. And somewhere out there, new echoes are still forming, light beams racing through the void, waiting to illuminate the next hidden corner of this cosmic crime scene. The explosion may be over, but its story, that's still being written, one reflected photon at a time. Among the countless stars in the Small Magellanic Cloud, 2 celestial vampires lurk in plain sight, HV2112 and HV11417, blue stragglers so unnaturally youthful they defy the laws of stellar aging. These aren't ordinary stars burning through their fuel at a steady pace. They're cosmic con artists stealing mass from neighboring stars to cheat death and extend their lifespans far beyond what nature intended. The result, stellar anomalies glowing with a brilliant blue hue, outshining their peers as if time itself has skipped over them. The secret to their eternal youth is as brutal as it is ingenious. Both stars are locked in close binary systems, their gravitational claws sunk deep into the flesh of their companions. Slowly, mercilessly, they siphon hydrogen-rich material from these neighbors, funneling stolen fuel into their own cores like cosmic thieves. Each gulp of gas reignites their nuclear furnaces, granting them a second or third or fourth lease on life. Over millennia, this slow-motion robbery reshapes both stars. The donor grows dimmer, its outer layers stripped away, while the vampire grows hotter, bluer, and more luminous, masquerading as a newborn star despite its advanced age. But these aren't gentle exchanges. The process is violent, messy, and often catastrophic. HV2112's feeding frenzy, for instance, has left its companion star deformed, its atmosphere stretched into a teardrop shape as material funnels toward the vampiric predator. In HV11417's case, astronomers have detected erratic flares, bursts of X-rays suggesting the stolen gas doesn't always flow smoothly but crashes onto the blue straggler's surface in unstable waves, triggering thermonuclear tantrums. What's truly eerie is how these stars mirror myths from human history, like the legends of undead creatures sustaining themselves by draining the life from others. Blue stragglers thrive by consuming their partners. But unlike folklore, this isn't fiction. Telescopes have caught them in the act, their spectral lines betraying the chemical fingerprints of stolen material. The victims, stripped of their hydrogen, often end up as faint, helium-rich husks, stellar ghosts haunting their revitalized predators. Yet these vampires weren't always monsters. Both likely started as modest stars, their paths altered by sheer cosmic misfortune. HV2112 may have once been part of a stable triple system until a gravitational kerfuffle threw it into a deadly embrace with its current meal ticket. HV11417, meanwhile, might have been born into an already tight orbit, its fate sealed from the beginning. Their transformations reveal a universal truth. In the unforgiving economy of star clusters, where resources are finite and competition fierce, survival sometimes means taking rather than sharing. And the aftermath, these stolen years come at a price. The more mass HV2112 and HV11417 accrue, the faster they burn through their ill-gotten fuel. Their brilliance is a facade, a fireworks display destined to end in spectacular collapse. One day, their cores will grow so heavy they'll implode, possibly triggering supernova that'll outshine entire galaxies, a fittingly dramatic end for stars that lived by cosmic theft. For now, they continue their slow feast, flickering against the backdrop of the Small Magellanic Cloud like forbidden jewels. They're reminders that even in the vastness of space, survival isn't always about playing fair. Sometimes it's about outlasting, outstealing, and rewriting the rules of existence itself. Deep in the frigid heart of the Small Magellanic Cloud, there's a cosmic time capsule so untouched by time it feels like stepping into the universe's freezer. HCN 0.009-0.044. A gas cloud so cold it defies the very concept of motion. This isn't just another wisp of interstellar material. It's a fossil suspended in stasis, a pocket of the early universe preserved with near-perfect fidelity. At a bone-chilling 1 degree above absolute zero, colder than the void between galaxies, this cloud's molecules move with glacial slowness, their thermal energy so sapped they practically vibrate in place. But the cold is just the beginning of its strangeness. HCN 0.009-0.044 is a chemical paradox, a relic swimming in molecules that shouldn't survive in the modern cosmos. Its spectral signature reveals an abundance of hydrogen cyanide, carbon monoxide, and even traces of formaldehyde compounds that typically get shredded by interstellar radiation or chewed up by star formation. Yet here they linger, pristine and unaltered, like ingredients in a cosmic pantry sealed since the universe's infancy. The cloud's chemistry is so archaic it mirrors conditions from the epoch before the first stars ignited, when the cosmos was a simpler, quieter place. What's truly baffling is its stillness. Most gas clouds in the Small Magellanic Cloud are turbulent cauldrons, stirred by supernova shockwaves or the gravitational pull of passing stars. But this one, it's eerily placid, its molecules barely disturbed over billions of years. Radio telescopes mapping its structure find no ripples, no clumps, no signs of collapse, just a smooth, diffuse veil hanging in space like a ghostly curtain. Some researchers compare it to a cosmic air bubble, trapped in a pocket of spacetime where the chaos of galactic evolution never reached. Theories about its preservation range from the elegant to the wildly speculative. One camp argues the cloud is shielded by an unseen barrier, perhaps a magnetic cage or a shell of dark matter, that deflects disruptive forces. Others propose it's a refugee, ejected from the depths of a primordial gas cloud so early in cosmic history that it never encountered the turbulence of later epochs. The most tantalizing idea, that HCN 0.009-0.044 is a rare remnant of the Dark Ages, the mysterious period after the Big Bang but before stars lit up the universe. If true, studying its chemistry could reveal the raw ingredients that birthed the first stellar generations. Yet the cloud's future is as uncertain as its past. One stray shockwave, one close encounter with a passing star, and this delicate relic could shatter like a snowflake in a furnace. For now, it remains a silent witness to a time when the universe was younger, simpler, and far, far colder, a frozen whisper from the dawn of everything. Tucked away in the sparse outer reaches of the Small Magellanic Cloud, there's a cosmic doppelganger that seems to defy logic. NGC 456, a barred spiral galaxy so eerily similar to our own Milky Way it feels like staring into a distant mirror. This isn't just any galaxy, it's a structural anomaly, a near-perfect replica of our home spiral complete with sweeping arms, a bright central bar, and even star-forming regions that twinkle like familiar landmarks. The resemblance is uncanny, as if some celestial artist sketched our galaxy from memory and left the draft floating in this dwarf satellite's outskirts. But here's what makes it truly bizarre. Barred spirals like this are vanishingly rare in the Small Magellanic Cloud. In a galaxy known for its chaotic, irregular shapes, NGC 456 stands alone, a cosmic aristocrat in a sea of anarchists. The mystery begins with its isolation. Most galaxies of this size and complexity orbit larger hosts, their structures sculpted by gravitational interactions over billions of years. Yet NGC 456 drifts in unsettling solitude, far from the turbulent tides that typically shape barred spirals. Its arms coil with a symmetry that suggests an untouched existence, as if it formed in a vacuum, free from the collisions and mergers that usually twist galaxies into such precise forms. Some astronomers speculate it's a survivor, a relic from an earlier epoch when the Small Magellanic Cloud was richer in gas, allowing this rare structure to emerge unscathed. Others wonder if it's an interloper, a wandering shard from another galaxy group that somehow found its way here, carrying its Milky Way blueprint across the void. Then there's the puzzle of its star factories. Peer at the spiral arms through infrared eyes, and they glow with stellar nurseries that mirror our own galaxy's Orion Nebula in both scale and brilliance. But the Small Magellanic Cloud's metal-poor environment should make such prolific star formation nearly impossible. Normally, the lack of heavy elements stifles the birth of massive stars and the vibrant clusters they illuminate. NGC 456 laughs at these limitations, its arms bursting with young, blue stars that sparkle like diamonds against the darkness. The solution might lie in its central bar, a dense, rotating backbone of stars and gas that funnels material inward, compressing it into new stellar generations with ruthless efficiency. It's a self-sustaining engine, a cosmic conveyor belt that defies its surroundings. What truly haunts researchers, though, is the timing. The Milky Way's barred spiral structure is thought to be a relatively recent development, emerging as our galaxy matured over billions of years. Yet here, in this tiny satellite, NGC 456 flaunts a similar design, as if both galaxies followed the same evolutionary script despite their vast differences in size and environment. Are the forces that shape galaxies more universal than we thought? Or is this mirror image just a fleeting coincidence, a trick of perspective that'll unravel with deeper observation? For now, NGC 456 remains a riddle wrapped in starlight, a reflection that raises more questions than answers. Its very existence challenges our assumptions about how galaxies form and evolve, proving that even in the farthest corners of the cosmos, familiarity can be the strangest discovery of all. Somewhere in the depths of the Small Magellanic Cloud, a dead star screams into the void, but this isn't just any stellar remnant. SGR 0526-66 is a magnetar, a cosmic maelstrom so magnetic it could erase your credit cards from halfway across the galaxy. Imagine a neutron star, already one of the universe's most extreme objects, cranked up to 11. Its magnetic field 1,000 trillion times stronger than Earth. That's not just powerful, it's reality warping. The forces at play here are so intense they literally twist the star's crust, creating starquakes that release energy equivalent to 1 billion hydrogen bombs in milliseconds. But what makes this magnetar truly unforgettable isn't its strength. It's the song it sings in gamma rays, a haunting cosmic melody that once shook our entire solar system. Rewind to March 5, 1979, and astronomers witnessed something unprecedented. A gamma ray burst so bright it saturated detectors across Earth's orbit, bouncing off the moon and back to our planet like a cosmic echo. The source, SGR 0526-66, announcing its existence with the loudest stellar shout ever recorded. For 1/10 of a second, this magnetar outshone every other object in the known universe combined, its burst detectable across intergalactic space. Today, we know that explosion was a starquake, the magnetar's crust snapping like a cosmic rubber band under unimaginable magnetic stress. But the aftermath was even stranger. The burst was followed by precise, fading pulses every 8 seconds, the star's rotation period creating what scientists now call the ringing of a magnetar, a celestial bell tolling across the light years. Now listen closer. Modern X-ray telescopes have caught SGR 0526-66 humming with something even more extraordinary: quasi-periodic oscillations, or QPO. These aren't random bursts, but distinct vibrational frequencies. Think of them as musical notes created when the magnetar's crust vibrates like a gong after a starquake. Convert these vibrations into sound waves, and you'd hear an eerie, almost organic pulsing, rising and falling like the world's most ominous synthesizer. The lowest frequencies correspond to oscillations rippling across the entire star's surface, while higher pitches reveal cracks propagating through its crust. It's a direct sonification of stellar violence, a concert played on an instrument 20 kilometers wide with the mass of 2 suns. What makes these songs so valuable is what they reveal about matter under conditions impossible to replicate on Earth. The vibrations act like cosmic ultrasound, letting scientists probe the magnetar's internal structure. The data suggests its core might be a bizarre quantum soup of neutrons and protons, while the crust could be a crystalline lattice 10 billion times stronger than steel, yet still brittle enough to snap under magnetic strain. Some theories even suggest parts of the interior might be frictionless superfluids, flowing without viscosity like liquid helium at absolute zero, but at stellar densities. Yet the biggest mystery remains why SGR 0526-66 is so active when most magnetars fade into silence after their youth. Located inside the Supernova Remnant N49, itself a spectacular debris field from the star's explosive death, this magnetar seems to be feeding off its environment, perhaps siphoning material from the remnant or drawing energy from magnetic field lines tangled in the wreckage. Every few years, it erupts anew, reminding us that death in the cosmos isn't an ending, but a transformation into something equally wondrous and terrifying. Somewhere out there, right now, this stellar zombie still sings, its gamma-ray area carrying secrets about the universe's most extreme physics, waiting for us to decipher the notes. In the shadowy outskirts of the Small Magellanic Cloud, there's a celestial phantom that defies conventional observation, ESO 51-9, a star cluster so cloaked in dust it's practically invisible to optical telescopes. Stare at its coordinates through visible light filters and you'll find nothing. Just an empty patch of sky, a void where stars should be, but switch to infrared and the truth erupts into view. A dazzling congregation of stars blazing through the cosmic fog, their light finally unmasked after traversing an interstellar veil thicker than a nebula's heart. This isn't just a hidden cluster, it's a lesson in the universe's sleight of hand, proving that some of its greatest treasures lurk just beyond the limits of human sight. The secret to ESO 51-9's near invisibility lies in its shroud, a dense, swirling cloak of cosmic dust that absorbs and scatters visible light like a celestial blackout curtain. Each photon attempting to escape the cluster's core must battle through this oppressive haze, with only the longest infrared wavelengths emerging unscathed. What makes this dust shell so unusual is its origin. Unlike typical nebulous veils, which drift independently of star clusters, this one seems intimately tied to ESO 51-9's stellar population. Spectroscopy reveals heavy elements like silicon and carbon woven into the dust, a telltale sign that these particles were forged in the atmospheres of the cluster's own aging stars, then expelled into space through stellar winds or violent eruptions. The cluster, in effect, has wrapped itself in its own funeral shroud, a self-made prison of its creation. But peer deeper, and the infrared portrait becomes even more fascinating. Spitzer Space Telescope images reveal the cluster's true scale, a sprawling metropolis of stars, many of them red giants burning with the slow, steady glow of advanced age. Their collective heat bathes the surrounding dust, causing it to glow at mid-infrared wavelengths like embers in a cosmic campfire. At the cluster's core, however, lurks a surprise, a handful of massive young stars blazing with unexpected intensity. Their presence suggests ESO 51-9 isn't just an ancient relic, but a dynamic hybrid where multiple generations of stars coexist, a rarity in such dust-choked environments. Theories about how this ghost cluster formed read like cosmic detective stories. One camp argues it was born in a particularly dense molecular cloud, its stars forever veiled by the remnants of their natal cocoon. Others propose a more dramatic history, that ESO 51-9 formed during a collision between two gas clouds, the resulting shockwaves compressing dust into this near-impenetrable barrier. The most tantalizing idea, that the cluster's dust is the accumulated debris of countless stellar deaths, a graveyard of supernova ejecta and planetary nebulae that's grown thicker over billions of years. Detecting such an elusive object required astronomical ingenuity. Traditional star cluster surveys reliant on optical telescopes completely missed ESO 51-9 until infrared astronomy matured. Modern instruments like the James Webb Space Telescope can now pierce its dusty veil with ease, mapping its stellar population in stunning detail. But the real breakthrough came from combining wavelengths overlaying infrared data with radio observations of carbon monoxide molecules in the dust cloud, creating a three-dimensional map of the obscuring material. This multi-wavelength approach revealed the dust isn't uniform but patchy, with some regions thin enough to glimpse the stars behind them, like frayed spots in a cosmic curtain. What makes ESO 51-9 so captivating isn't just its invisibility, it's the reminder that the universe often hides its wonders in plain sight. For every glittering star cluster we admire in visible light, there could be a dozen more lurking just beyond our natural vision, their stories waiting to be told in the infrared whispers we're only now learning to decode. This ghostly gathering challenges us to look deeper, question assumptions, and remember, sometimes the most profound discoveries aren't made by seeking new objects, but by seeing old skies in a new light. At the edge of the Small Magellanic Cloud, there's a place where the stars simply stop, SMC-30, nicknamed the Gateway Void, isn't just another empty patch of space. It's a perfect spherical abyss stretching over 200 light-years, its edges so sharply defined they look like they were carved with celestial precision. Peer into this darkness, and you won't find the usual dust clouds or dim red dwarfs that litter most galactic voids. Instead, there's nothing. A literal nothingness so absolute it feels like a hole punched clean through reality itself. What could carve such a void? One theory points to a black hole's gluttonous past. Imagine a supermassive black hole, one of the universe's most efficient cosmic vacuum cleaners, passing through this region millions of years ago. As it moved, it would have devoured every star, gas cloud, and stray photon in its path, leaving behind this eerie spherical desert. The math checks out. A black hole with the right mass and velocity could theoretically clear a cavity this size, but there's a catch. No remnant black hole remains at the void's center. No X-ray emissions, no gravitational wobbles in nearby stars, just silence. That absence has spawned wilder ideas. Some theorists suggest the Gateway Void might be the shadow of a wormhole, a tunnel through space-time so stable its gravitational lensing effect could bend light around it, creating the illusion of emptiness. In this scenario, the void wouldn't be empty at all, but a portal disguised as nothingness, its true nature hidden by the very physics that sustain it. The perfect spherical shape lends weight to the idea. Natural cosmic phenomena rarely produce such geometric precision, but a wormhole's event horizon just might. Then there's the unsettling symmetry. Most voids in space are irregular, their edges blurred by stellar winds or supernova shockwaves. But the Gateway Void's boundary is razor-sharp, as if someone drew a circle with a protractor on the fabric of the cosmos. This unnatural smoothness has even prompted whispers of extraterrestrial engineering. Though most scientists dismiss this as fantasy, the void's precision does demand an explanation beyond ordinary astrophysics. Perhaps the most haunting detail is what lurks just outside the void's edge. A thin shell of young, blue stars traces its circumference like a glowing hula hoop, their formation dates clustering suspiciously close to the same epoch. This suggests a cataclysmic event, perhaps the same one that created the void, triggered a synchronized burst of starbirth in the surrounding gas. It's as if the universe tried to paper over the wound with new starlight, a cosmic scar tissue that only deepens the mystery. The Gateway Void doesn't just challenge our understanding of space, it confronts us with the limits of our imagination. Is it a relic of destruction, a shadow of higher dimensions, or something we haven't even conceived yet? Every telescope pointed at this darkness sees only absence, but sometimes what's missing speaks louder than what remains. The Small Magellanic Cloud isn't just a dwarf galaxy, it's a cosmic contortionist, bent and twisted into surreal shapes by forces beyond its control. If you could step outside our Milky Way and gaze down, you'd see it warped like a fishhook, its stars and gas stretched into long, shimmering tidal streams that trail off into the void. This isn't some random deformity, it's the brutal handiwork of gravity, a relentless tug of war between the Small Magellanic Cloud and its colossal neighbors, our Milky Way and the Large Magellanic Cloud. Over billions of years, their gravitational pull has yanked this tiny galaxy in opposite directions, turning it into a living lesson in celestial torture. What's unfolding here is more than just a slow-motion demolition. It's a cosmic puppet show where invisible strings pull everything out of place. The Milky Way's tidal forces don't just distort the Small Magellanic Cloud's outer edges. They reach deep into its heart, skewing the orbits of stars, gas clouds, and even mysterious objects like rogue black holes. Picture a snow globe shaken violently, its glittery contents swirling in chaotic patterns. That's the reality for stars inside the Small Magellanic Cloud. What should be orderly orbits become spiraling, erratic paths, some flung outward into tidal streams, others compressed into bizarre, elongated loops around the galaxy's core. These warped orbits aren't just academic curiosities, they're the reason we see so many impossible objects in this dwarf galaxy. Take those hypervelocity stars racing toward intergalactic space, or globular clusters spinning faster than they should. Their strange behavior traces back to the galaxy's distorted gravity field, a hall of mirrors environment where the usual rules break down. Even nebulae like the Crimson Eye or DEM L50, they're asymmetrical shapes to these tidal forces. They're gas sculpted by the same gravitational currents that twist the galaxy itself. But the most dramatic evidence of this cosmic wrestling match lies in the Magellanic Bridge, a faint gossamer trail of hydrogen gas linking the small and large Magellanic Clouds like a celestial umbilicus. This bridge didn't form peacefully. It's the scar of a close encounter roughly 200 million years ago when the two dwarf galaxies grazed each other, ripping out gas and stars in their wake. The aftereffects still ripple through the Small Magellanic Cloud today, with some regions stretched thin as taffy while others pile up in dense, chaotic knots. Yet for all this violence, the galaxy refuses to surrender. Against all odds, it keeps forming stars, though not where you'd expect. Tidal forces have compressed pockets of gas along its eastern flank, triggering frenzied bursts of starbirth in regions that should be too disrupted for such activity. It's as if the Small Magellanic Cloud is fighting back, turning its own destruction into creation, one stellar nursery at a time. The final twist: this isn't a one-time event. Every pass near the Milky Way or its larger sibling peels away another layer, ensuring the Small Magellanic Cloud will keep evolving or unraveling for eons to come. Astronomers suspect it may not survive as a coherent structure forever. Eventually, the tides could tear it apart entirely, leaving behind only streams of stars adrift in the Milky Way's halo. For now, though, it remains a masterpiece of gravitational artistry, a reminder that even in the vastness of space, no island is ever truly alone. One of the most baffling riddles hidden within the Small Magellanic Cloud isn't about what's there, it's about what isn't. Dark matter, the invisible scaffolding that holds galaxies together, seems to be vanishing from this dwarf galaxy at an alarming rate. For decades, astronomers assumed the Small Magellanic Cloud, like all galaxies, was cocooned in a hefty halo of dark matter. But recent observations have thrown that assumption into chaos. Measurements of stellar motions and gas dynamics suggest this galaxy might contain as little as 1/10 the dark matter predicted by standard models, a cosmic anomaly that's sending shockwaves through astrophysics. The evidence comes from the galaxy's rotation curve, a fundamental tool for mapping a galaxy's mass. Normally, stars on the outer edges of a galaxy orbit much faster than visible matter alone can explain a discrepancy attributed to dark matter's gravitational pull. But when researchers charted the velocities of stars in the Small Magellanic Cloud, they found something startling. The outer stars aren't moving as fast as they should. Instead of the curve flattening or rising as you'd expect with a dark matter halo, it drops off as if the galaxy's hidden hand has let go. Some regions even show stars moving slower than models predict, like runners losing steam in a race with no finish line. This isn't just a minor accounting error. It's a direct challenge to the lambda cold dark matter model, the reigning framework for understanding cosmic structure. If the Small Magellanic Cloud truly lacks dark matter, it could mean our theories about how dwarf galaxies form are fundamentally flawed. One radical explanation proposes that the galaxy never had much dark matter to begin with. Instead, it might be a tidal dwarf, a structure born from gas and stars ripped away during a past collision between the large Magellanic Cloud and the Milky Way. Unlike traditional galaxies, which form within dark matter halos, tidal dwarfs assemble from recycled visible matter, leaving them oddly lightweight. But there's a catch. The Small Magellanic Cloud's current shape and star-forming regions don't perfectly match simulations of tidal dwarf formation. Its structure is too coherent, its history too complex. This has led to a wilder hypothesis that the missing dark matter wasn't stolen or absent, but somehow heated up and dispersed. In this scenario, repeated close passes with the Milky Way or its larger sibling could have scrambled the galaxy's dark matter halo, slingshotting it outward like marbles flung from a bowl. Supporters point to the Magellanic Stream, that faint ribbon of gas trailing the two dwarf galaxies, as potential evidence of this gravitational turmoil. Not everyone's convinced, though. Skeptics argue the anomaly might be an illusion caused by the galaxy's extreme distortion. After all, the Small Magellanic Cloud isn't just warped, it's actively being torn apart. Traditional methods for measuring dark matter assume a stable, symmetrical galaxy, but this one's more like a taffy pull in progress. If astronomers are misreading its true shape, they could be underestimating its mass. Others suggest the answer lies in modified gravity theories like modified Newtonian dynamics, which tweak the laws of physics to eliminate the need for dark matter altogether. What's at stake isn't just one galaxy's composition, it's our understanding of the universe's hidden architecture. If the Small Magellanic Cloud's dark matter deficit is real, it could mean dwarf galaxies come in flavors we've never imagined. Some might be dark matter-dominated fossils from the early universe, while others, like this one, could be later arrivals built from the scraps of cosmic collisions. Every telescope trained on its faintest stars, every simulation of its turbulent past, brings us closer to an answer. Until then, this quirky little galaxy remains a living experiment, one that might force us to rewrite the rules of gravity itself. From rogue planets exiled into the eternal dark to zombie stars that refuse to die, from cosmic jellyfish sculpted by supernova shockwaves to magnetars singing in gamma-ray frequencies, the Small Magellanic Cloud isn't just a gallery of celestial oddities. It's a cosmic laboratory where the universe tests the limits of physics, rewrites the rules of existence, and quietly mocks our assumptions about what's normal in space. Think about it. We've seen star clusters flung across the void at unimaginable speeds, nebulae glowing with forbidden colors, and entire galaxies warped like taffy in the grip of invisible forces. These aren't exceptions to the rules, they are the rules, revealing a universe far wilder than our textbooks ever dared suggest. What makes these 30 objects so extraordinary isn't just their strangeness, it's how they force us to rethink the very fabric of reality. Take the Crimson Eye Nebula, where a dying star defies the Small Magellanic Cloud's metal-poor chemistry to paint the cosmos in blood-red light. Or the ghost cluster ESO-5 1-9, hiding in plain sight behind a self-made curtain of dust. Even the gateway void, that eerie spherical nothingness, challenges us to ask, are we staring at a cosmic accident or evidence of phenomena we can't yet comprehend? Every observation peels back another layer, proving that normal is just a word we use for the mysteries we haven't solved yet. Now it's your turn. Which of these cosmic rebels captured your imagination? Was it the vampiric blue stragglers stealing life from their stellar neighbors, the supernova echoes of 1987A still whispering across the light years? Or maybe the taffy galaxies locked in their slow-motion dance of destruction and rebirth? Drop your favorites in the comments. I'd love to hear which oddities left you awestruck. And if you think we've missed something even stranger lurking in the Small Magellanic Cloud, shout it out. The universe is vast, and every discovery starts with a question. Before you go, here's a challenge. Step outside tonight and find the Small Magellanic Cloud with your own eyes. It's that faint smudge near the southern horizon, a flicker of starlight that survived collisions, explosions, and the relentless pull of gravity. Remember, you're not just looking at a dwarf galaxy, you're seeing a cosmic frontier where the rules bend, the impossible thrives, and every shadow could hide the next great mystery. So keep wondering, keep exploring, and never stop looking up. The universe's strangest stories are still being written, and who knows, the next one might have your name on it. Until then, stay curious, fellow stargazers. The cosmos isn't done surprising.